So I don't want to make that statement because that statement can't possibly be true. So this is typically sort of a Griffiths effect sort of thing. And typically what people do to get rid of this effect, they say, look, let's not do that. Let's take the median, or let's average the log of the bond dimension, or something like that, so that rare instances where this is not true, rare instances where the bond dimension needs to be big because sneakily the system isn't disordered, don't screw up my average. Okay, so that is in the sense in which I mean the bond dimension D doesn't grow. It is in the sense where I do an average, or I take a median, or I do something so that the occasional exponentially large answer doesn't mess up my, my result. The typical case is the bond dimension is small. There are, of course, rare instances because I'm doing a disordered average where it's not. I don't want those rare instances to dominate the average. Okay, so I won't say that over and over again. When I say the bond dimension is small, that is what I mean. Any questions about that?
Sorry, so what do you mean by average D? You're just saying I need to do some D for this sort of configuration.
Right, so I'm going to do a million disorder configurations, and then I'm going to average them.
For each one, fixed D.
For each one has a fixed D. And then I say, look, that average, if I make my system 10 times bigger, I like it to be the same number. So I do a million, I do W of 4, I do a W of 6, I do a million configurations, and I say, oh, D is 1,000 for 10 sites. And now I want to do it for 100 sites, and I like D to be 1,000 too. But that's not true because there are some rare instances where I saturate the bond dimension. So it's sort of 2 to the 10 and then 2 to the 100. And that just screws up my average. But that's somehow, that's an atypical case. It's sort of a rare instance that's screwing my average up. That's not what we want to think about. Let's think about the median, or let's think about the average of the log. Let's do something where occasional rare instances where D is very large don't screw up my average. This is a common trick when you have sort of Griffiths effects, these rare instances screwing up your average.
Sorry, the operator is actual bond.
No, just bond dimension, it's just a number. A million. A scalar, it's just a number.
Sorry, why is D large when you choose all of the HI to be equivalent?
Well, because then you might as well be 0. That's a disordered distribution. And so now we're not in the many-body localized phase, we're in the ergodic phase. Generically, if you're in an ergodic phase, you have huge entanglement. I mean, it's a 0th order in the ergodic phase. There's nothing special about an eigenstate. And so it's like I pull a state randomly out of Hilbert space. And we know generically if I pull a state randomly out of Hilbert space, just by counting, it must be true that it requires a lot of numbers to describe it. Just by counting, there are lots of states, they must require a lot of numbers. Yeah.
So isn't here, are you getting D in each disorder realization by fixing completion?
Sorry, I can't hear you.
Are you getting D for each disorder realization by fixing completion? Or
Yeah, so what I'm doing is for a given disorder realization, you choose your HIs, that tells you the realization. Then you figure out what these G's and E's are. You compute this D, and then you do it over again a million times and you average. And now I'm not averaging D, I'm averaging log D.
how are you computing these?
That's, I mean, let's say for the moment that I figure out what the G's and E's are and just measure it. I'll give you a real answer in half an hour or something. But it's exactly the same as, this is what we're doing. We're figuring out what the G's and E's are, we're measuring how big they are. And that's what we're doing. I mean, the G's and E's are just matrices, and we just measure the size of the matrix. Great. Other questions?
And how do we know that D doesn't change the size of the system?
We don't. I'm making that. I'm telling you it's true. And I will. How do we know it's right? In a little bit, I'll have a better answer to how we know that. But it's still going to be essentially. It's plausible, and we measure it. And the combination of there's a physics argument and we numerically measure it, and it doesn't go up. And it's sort of implied by other things we believe about MBL will tell us that almost certainly it doesn't. It's not a rigorous proof. It's not like I have a mathematical rigorous statement, but there's a physics argument and there's a numerical argument.
What it's basically saying is that even if we add the lower lattice size, if there is an MBL phase, then because the phase is localized in a region, you don't add more eigenstates.
It's morally speaking saying that to describe the eigenstate, you don't have like a combinatorial explosion of the number of numbers you need. But yes. I mean, that's true here, right? In this extreme pathological limit, if my state gets longer, it's not like I need now 2 to the n number to describe it. I just need to tell you each site whether the spin is up or down. So it's no different in this case. It's just kind of surprising that it works in general. Yes?
Matrix square states work for ground state systems that not made by localized, right?
Yes.
So is it possible to have an ergodic phase and some class of excited states that could be well described by the same ideas, not by transspectral, but some class? Is that possible?
Yeah, in fact, that's generically true of any gap phase for low-lying excitations. It's generically true also for like MBL phases that are not fully MBL that have a mobility edge for the part of the mobility edge that's not ergodic.
So you can do something there, not
You-
full thing, but something.
That's right. You can do something there, but it won't be describing the ergodic part of the spectrum.
But it may be, you said it may be near the mobility edge.
I'm sorry?
You said it could be near the mobility edge if the states are gapped.
Yeah, you can do something like this to describe states near that are sort of in the MBL parts of the mobility edge. Okay. Yes. Other questions? Okay, good. Let me also make one more statement here about the gauge freedom. So I told you this, but it turns out, as I said, that not only do you have to choose the ground state matrices for G, but you've got to choose them in a special representation. And this ends up being technically annoying, but it turns out that there's lots of G's that represent the same ground state. So let me just motivate why that is. So if you imagine I have these G's, I say, look, I'm going to essentially multiply the middle here by the identity, U dagger, for some arbitrary U. And then I take this U and multiply G1 up by this U and G1 down by that U. And I take this U dagger and I multiply U dagger G2 down and U dagger G2 up. And I say, good, this is the new G1s and this is the new G2s. So after a moment's reflection, what you should appreciate is that for any configuration, this is going to give the same number. I say up, up, down, down. You say, well, that's G1 dagger times U times U2 dagger times G2 down times up. Well, I multiply U dagger in the middle. Those U daggers go away. The identity. And so what I'm telling you is that one can change what these G's are and still have the same ground state wave function. And so what I'm telling you in addition is that for this thing to be true, you have to have chosen special G's and special E's. So you can't choose any of the ground state G's, you have to choose a special set of them. In a little bit, we'll see what that special set is. But that's sort of an important detail. Okay, so I've now largely unpacked what claim 1 means. Let me just spend a couple minutes telling you some implications of claim 1. So we know from the phenomenology of the many-body localized phase that there are some things that are true about MBL systems. So for example, one thing that's true is that the eigenstates obey an area law. Now, that follows completely trivially from what I've just said. I just told you that all eigenstates can be represented by matrix product states of finite bond dimension. Matrix product states of finite bond dimension, by definition, obey an area law. Okay, so that's a trivial implication. A slightly less trivial implication is, for example, thinking about the failure to thermalize. So one of the things you know about the phenomenology of MBL is you know that MBL states don't thermalize. And so now we're going to ask ourselves, can we use the fact that this is the structure of many-body localized states to understand that, this is the structure of the excitations of the MBL system to understand why things don't thermalize. So to do this, you have to know another fact about MBL states, matrix product states. Matrix product states, all the correlations decay. and exponentially fast. And in fact, if I have some, let's see. So let's consider this question of thermalization. So imagine that I have some eigenstate. And what I do is I kick that eigenstate over in the left half of the system. Okay, so now if I kick that eigenstate over the left half of the system, what that's going to do is that's going to instantaneously change something about this eigenstate over here. So instead of being what it was, I don't know, let's say it's some C tilde here. So not an eigenstate anymore, it's just some alternate state that's instantaneously changed. And now what we should do is we should say, look, what happens when I do unitary time evolution of this state? Well, what we should do is we should write this new state, which is no longer an eigenstate, as a linear combination of eigenstates. And then we should unitarily time evolve all of them. And I'm not going to go through this in gory detail, but what shouldn't surprise you, because everything in matrix product states decay exponentially, and these are all finite bond dimension, is that up to some exponential corrections, all of the excited states that have overlap with this MPS are going to look the same over here. Now over here, maybe they're going to look different. Who knows what they look like kind of in that chunk of the system. But once you get far enough away, these matrix product states are all going to have the same structure. And so now, when I begin, there's some amplitude in front of each of these, right? Alpha naught, alpha 1, alpha 2, etc. Now when I begin doing unitary time evolution, all I'm doing is I'm rotating the phases of each of these individually. But what ends up happening is that nothing over here is changing, right? Because I only overlap with matrix product states that were essentially the same that was in a distant place. And so what that's telling you is that's telling you that if I compute observables over this chunk of the system, because observables all decay exponentially fast, what I'm going to end up finding is I'm going to end up finding that nothing over here changes. So despite the fact that I kicked it over here, I've dumped a bunch of energy into the system over here, that energy can't move to that chunk of the system. That chunk of the system has to locally look the same as it always had. Okay, so I'm sort of hand-waving here, but one can think about this sort of more carefully, and this is sort of the picture that arises from this. Is there any questions?
Alpha and alpha, those are basically C and T bar are not eigenstates at the moment.
Yeah, well, this whole thing is not an eigenstate, and yes, these matrices are not the GP matrices that make up eigenstates, they're just something. Maybe it changes this one a little bit too, who knows. But the point is you have a new matrix product state that differ over the edge, and then you argue, look, this matrix product state which differs over at the edge is not going to overlap. We know what all the eigenstates look like. They all look like this. We can go compute overlaps, and what we're going to find is we're going to find that it has high overlap with things that have changed on the left, but everything on the right is mainly going to stay the same. Great, other questions?
But this also assumes that there is no long-range transport.
Well, it doesn't assume that. It says, look, we believe the claim is that the eigenstates are described in this way. And if that's true, and these are fixed bond dimension MPS, and MPSs that are different in this way, if this MPS has no overlap with an MPS that has like an E over here, then this follows.
Right, but in general, if you perform a local quench
Yes.
then the energy can be transported to much further.
It can, but what that means is that means there must be some structure of the eigenstates that are different from what's here. So certainly it's true in general. For example, if these eigenstates, if these states grew with system size, then in fact it would be true that you could sort of transfer some energy sort of non-locally, because correlation functions over here could then be affected by things over here, because the bond dimension grows. Great, other questions?
So how do you prove that for such matrix product states, everything decays exponentially? And even before that, what do you mean by things decay exponentially?
So for one thing I mean is that I mean all the correlations decay exponentially. So if you look at any correlation function, they're exponentially decaying. And in fact, what I mean in more detail is that the correlation function is something like I equals 1 to the bond dimension E alpha I x. is minus alpha by x. So if you allow this bond dimension to grow, then you can compensate for this exponential decay. Sum of an exponential number of exponentials could be polynomial. But if I fix the bond dimension, it's 20, then everything has to decay exponentially.
Sorry, what is x?
It's just the distance, the distance between two states.
And you get that kind of behavior for any operators or?
For any operators, for any MPS. This is essentially, MPSs are fancy AKLT states. The reason this happens is the same reason it happens in AKLT states. But one can prove this. One can essentially work out the transfer operator for what's going on. And one can see that the correlation functions of any MPS decays in the following way. Now, you can compensate for that if you're going to let D grow. If you sum an exponential number of exponentials, you can compensate for the fact that they're decaying exponentially.
Right, now how does this explanation that you are showing on the board fall from that claim?
It doesn't directly follow. You've got to be a little bit more careful. But what you should do is you should say, look, let me now begin computing the overlap of this thing with things that are very different. And what you see is that overlap goes to 0 very quickly. So it's not, I can't do it quickly enough to sort of write out on the board. But essentially, you have to understand the details of how you compute overlaps of MPSs. And what you'll see is you'll see that where these things are fixed bond dimension and disagree, that overlap is going to go to 0 very fast. One can check this numerically, for example. One can just play with G's and E's and see this. Yes?
So you get the short range correlations anytime you have a gap. So is that you get these MBL phases anytime you have a gap?
Say again?
Anytime you have a gap,
You get
have a short range correlation. So you get MBL anytime you have a gap, or like what's special about this order in this?
Yeah, so in MBL, you'll get these decaying correlations. I think the way you want to think about this is you want to go back to sort of this emergent integrability. If you're emergently integrable, what that really means is that means all the excited states are really fancy ground states. Because it means that your Hamiltonian is block diagonal in some ways. And if you're block diagonal, then what you expect is you expect that things that you thought were excitations are really sort of ground states of these other blocks. So that's at least one way of seeing what's going on. Good, other questions? So someone remind me what time I get to talk to?
Should be before 4:15.
5 minutes. Okay, I have 5 minutes is what you're saying.
Yes, 5 minutes.
Okay, good. Okay, so let's go on, and I've said most of what I want to say about claim 1. Let's go on and start thinking about claim 2. Claim 2 is essentially there's a short quantum circuit or an MPL, which I'll tell you what that is next time, which diagonalizes the MPL Hamiltonian. So let's just spend our 5 minutes thinking a little bit about the matrix that diagonalizes our Hamiltonian. Okay, so we have some Hamiltonian, and there is some unitary matrix which diagonalizes it. Good. Equivalently, there is a quantum circuit that is the unitary matrix that diagonalizes it. And something that one doesn't typically think very much about, but is nonetheless a true statement, is that there are many unitary matrices that diagonalize the same Hamiltonian, and those unitary matrices differ by some permutations of rows and columns, as well as some phases on the eigenvectors that make up that unitary matrix. And the reason you don't typically think about this is typically it doesn't matter, but when the name of your game is I want to understand how short the quantum circuit that represents U is, that starts to matter. And so we'll spend our 5 minutes trying to unpack and understand why that matters.